All right, let's begin on this about to be rainy afternoon. So we're continuing Epoch 4 of the course, which hopefully is a little less algebra intensive and maybe a little more interesting and applied. So today we'll do 4.3, which is optimization. And I think like last time on Monday, I'll say a few things at the beginning and remind you of a little bit of terminology. And then we'll just start doing some practice problems of various sorts, some graphical and some less graphical. So let me just remind you of one or two more things, and then we'll start doing some stuff. So function. All right, so let's say we have a function, as usual, f of x. And for some reason, we're only interested in the values on an interval. So x can't be just anything. There's some lower limit and then some upper limit for which the function is defined. Often, but not always, a might be 0. If you're doing some, I don't know, like a population model, you wouldn't ever have negative numbers or something like that. And we'll see some examples of this next week, where we're just interested in analyzing a function on an interval. And we might want to know things about where is this function largest and where is it smallest. So like, a situation might be like you have to spend at least $A, but you can't spend more than B dollars. What should you do? Something like that. So we have some local max. And here's a local min. So those would be critical points. A local max, you're at the top of a mountain. A minimum, you're in a valley. We also might want to know the global min. So like maybe you want to maximize, you get to choose any number between a and b, and you want to make this function as big as possible. Then you've got two maxes to choose from, but you would want to choose this one because it's bigger. So we call that the global max. OK, so far there's not really anything new, but now here comes one new thing. So what if you wanted to minimize the function on the interval? What would you do? Can you repeat, sorry? If you wanted f of x to be as small as possible, and you're only allowed to go from a to b, what x value should you choose? B, yep. So we'll call this So if you're analyzing a function that's defined on an interval and you want to know the largest and the smallest values, it's now sort of a two-step process. You find the derivative, set the derivative equal to 0, solve for x, which we've been doing for homework and we did last week, and that'll find these critical points. But it won't tell you anything about the endpoints. So you'll also need to make a graph or plug in the value of the function on the endpoints to check to see if the endpoints are lower than maybe a local min. And as a practical matter, often you would just make a graph on a computer or calculator and then just analyze the function and see what's going on. And if, it looks like this endpoint is lower than that thing, then you might want to investigate this endpoint. So I think that's all that I want to say. Yeah. OK, so you're ready to do this now? OK. So let's try problems 1 and 2. These will take a while. We might not get through all these on the sheet, but that's fine. All right, so we're analyzing this function. And we need to do two things. We need to check to see if they're critical points. any wiggles, any mountains or valleys in the middle, and then we also need to check out what's going on in the endpoints. So first we'll look for critical points. To do that, I need to find the derivative. Then to find the critical point, I set the derivative equal to 0, and I solve for x. And I would recommend writing this out. It's not a lot to write, but it's, you're sort of shuffling back and forth between functions and derivatives. OK, so take the derivative, set it equal to 0, solve for x, and I get 3. And then I wonder, is this a min, a max, or a neither? Those are the possible types of critical points. And I decided it was a minimum by making a graph. We know, OK, so I know that there's going to be a minimum, or there's a critical point at 3. Because the leading term is positive, I know it's an upward opening parabola. So I figure it has to be something like this. I guess it could be below the axis, but I drew it above the axis, and it turned out that that worked. But you can also do it in a calculator or in Wolfram Alpha. All right, so then we need to answer these questions. What is the global min and the global max on these two intervals? So that means we want to know values of the function g. So I want to know what the value of g is at 3. That's the critical point. And plugging in, that turns out to be 2. And I also want to know what's going on in the endpoints, which are 1 and 4. So I plug in 1, and I did the arithmetic wrong, and then I do it correctly, and I get 6. And then I plug in 4, and I get 3. And that is consistent with this picture here. So along this interval, the largest value is going to be what's going on up here. So that would be 6. And the minimum would be 2. So global min is 2. Max is 6. Min and max, if we're just going from 3 to 4, now that's this little window. This now is a minimum, that's 2. The maximum is going to be what's going on over here on this edge, and that would be 3. So I'm hoping this seems a little simple and pedantic. I'm trying to read these various blank expressions. You're not as emotive as some of the other classes I have, where it's easier to read their stances. Also, and I mentioned this last time, but a reminder that likely many of you at some point in your life had to memorize formulas for turning points of parabolas, and now that stage of your life is gone because you know calculus, and you can just figure it out. So that's a nice part of growing up mathematically. Lots of, all sorts of pre-calc stuff that you had to memorize or was totally mysterious becomes understandable. It's calculus. All right, so let's bump ahead and do number 2. And depending on how that goes, we can just slide into 3 and 4 as well. All right, so we proceed similarly. We want to find critical points. So to find the critical points, we're going to need the derivative. So here I am calculating the derivative. And this is one of these product plus chain rule ones, all the greatest hits from Chapter 3. So I took the derivative of x, left that one alone, plus leave this one alone, take the derivative of this. The derivative of e to the blah is e to the blah. The derivative of blah is minus 4x cubed. So then I simplified a little. X and x cubed become x to the 4th. I factored out an e to the minus x to the 4th, and that gives me this. So now we're taking the derivative using chain and product rules. Then to find the critical points, we need to set the derivative equal to 0 and solve for x. So here we go. So here's the derivative, and I set it equal to 0. So let me say a few things about this step. And one of the reasons I chose this problem was there were a couple questions about this, a problem similar to this last night. So you've got something times something equals 0. So you've got two choices. Either this thing can be 0, or that thing can be 0. So I'm exploring this thing being 0 possibility. So I said, all right, so 1 minus x to the 4th equals 0. And then I did algebra and ended up getting down to here. And when you have an x to the fourth, what you're doing is you're taking the fourth root of both sides. And I thought about taking the square root twice. I don't know if that made things more or less complicated. But you should end up with 1 over square root 2. But then the other thing you have to think about is, wait, what happens if this is ever 0? And the answer is, well, this can never be 0. So e to the anything is never 0. Because exponents mean multiply by yourself some amount of times. And there's no way you can take a number, any number, e, 6, 7, 2, a half, and multiply itself by itself and end up with 0. So this thing will never be 0. Some of you dutifully thought, what, e to the minus, what is this, x to the minus 4 equals 0. And you said, oh, I know, I have to take the natural log. So you do natural log. And your calculator refused to do this, or it gave you an error. And so that's because there is the natural log of 0 is not defined. Because, right, remember, this is what the natural log looks like. It's one of those things on your right hand. It goes to negative infinity at 0. Anyway, so this was a dead end, or not really a dead. I don't know if it's a dead end. That implies like running into a wall. Maybe this is more like slowly walking into quicksand. Anyway, this was something a number of people did, understandably, but it won't lead you anywhere. OK, so let's go back to over here. So we find, yeah. Like, what do you mean? Sorry. Like, oh, this is sort of, let's see. So the answer is no, and let me think of a better reason than because. So this means you do x. This is the notation is somewhat ambiguous, but this notation means you do x, raise it to the fourth power, and then stick that in e. So you wouldn't get the same. You wouldn't get this. You wouldn't get the same thing. No, because.
If you tried drawing with parentheses, maybe that would help.
Yeah. So what this means is. Not Yep. No, that's a good question. I feel like there ought to be a better answer to this. I'll think about that when I'm pacing around when you're doing the next sort of exercises. OK, so we found a critical point, and now we need to classify it. And again, usually what I do is I'll make a plot. And here's making a plot. You can do it on one of your machines. And indeed, there's a maximum there. Then we'd like to know how tall the peak is. And to do that, we would have to plug 1 over square root 2 into this function, which I didn't even attempt to do in my head. Did anybody get a number for that? It's probably pretty small. 0.55? Yep. OK. At least democratically, that seems to be the answer. And OK. Yeah. Yeah. OK, so then on this interval, starting at 0 and going up to, but not including infinity, because infinity is not a number you can really go up to. The global max, well, that's 0.55. And what would be the minimum value on that interval? 0. Yep. All right. So let's see. So let's try problems 3 and 4, those will sort of some sketching problems. And then problem 5, start on that, but we'll surely need to talk it over. But spend a little while thinking about problem 5 before we talk through that one. All right, let's take a few minutes to talk through 3 and 4, and then see where people are at with 5. But first, 2 things. First, for the sake of the video and all the thousands of people who may watch this someday, that number should be this, not 0.55. Just correct that. And also something I keep meaning to mention. So homework help tomorrow. I'll be available 11 to noon. This is probably 11:10 or 11:15 is more realistic. So a little after 11, because I teach right until 11, up until noon in the dining hall, and then 2 to 3. And often I say things like, I can stay later if need be. I've got meetings at 3, and then 3:30 and 4, so I will actually have to leave at 3. Yeah, so Corey can't make it tomorrow, so I'm substituting for Corey.
I'll be there tonight from 6:30.
Oh, that's right, yep. So 6:38. Casey, OK, great. All right, let's see. So what were the specifications for these? Continuous function, local minima at 2 and 4, a global max at 3, and then no other extrema, so no other mins or maxes. And so in order to get a min, we have to have a valley, so it's going to have to be rising over here. To not have other extrema, this is going to have to asymptote out, just become flat. Similar story over here. A function with 1 inflection point at -2. Lots of different answers. Here it's going from concave up to concave down. And there are no critical points or anything. There's just 1 point of inflection. So there are lots of possible answers. If you did a sketch and you're not sure if it works, Casey or I can take a look at it and give an opinion. All right, so now let's imagine this semi-fictional cost curve. So this is cost in millions of dollars to educate S students. So you might think it would be like the cost to educate 0 students would be 0. But before you can even admit the first student, you would need to build a campus or something. So that might be like the cost of building the buildings. If you're thinking about like manufacturing something, before you even get to manufacture one item, you have to buy the equipment that manufactures the items. So anyway, and that's called a fixed cost. It's a cost you have to pay if you're going to manufacture 0 items or thousands and thousands of items. OK, so the average cost. What's sort of the form? I mean, how do you calculate an average cost? What would you do? What was that? I don't remember. Yeah, she takes how much it costs divided by the number of students. OK, so anytime you have a ratio like this, you could picture that as a slope of a line. This is some sort of rise over some sort of a run. And let's see. I'm probably going to make a mess of this figure pretty quickly. But so if we wanted to know what's the average cost per student if we have 100 students at this mythical small college, that would be the slope. OK, so this height is C. This height is, or this base is S. So the rise over run of this is C over S, and that's so the slope of this line is the average cost. So slope equals C over S equals average cost. And this starts off pretty flat. Once you've built the building and you've hired like a few faculty, you don't really need to add. There's no more expenses associated with like having 5 or 10 or 15 students. Anyway, so these things typically start off flat. So as I move along this cost curve, if I imagine a line connecting my fingers, that line, all right, starts steep. So there's a large average cost. If we just have, what are the numbers here? If we just had one student at this mythical school, it would cost $3 million to educate them. It's probably not a good business model. That's why there aren't many colleges with like one student, I guess. And as we move along this curve, the line gets less steep, but then eventually it starts to get more steep. So let's see. All right, so here's a line, and it's pinned here, and then I'm moving it. Imagine moving it along here, less steep, less steep. So average cost is going down, average cost is going down, average cost is going down till right about here. And then as I move along the line, average cost starts going up again. So the minimum cost per student, at least according to this graph, which is not at all accurate, would be between 200 and 300. And is that is it the same on the paper if I? Let me see. I get around 240, 250 maybe when I do it. So so there are a lot of optimization situations where the reasoning is done almost purely graphically, like this, as we did here. And there's some fun problems. At least I think they're fun. I hope some of you find them fun. Thinking about different sort of optimization things, sometimes in I guess, sort of animal behavior or ecology settings. So like there's optimal foraging theory. If you need to make small talk with Chris in the rain when you're out doing whatever goopy stuff you're going to be doing in the field trip, you can talk about optimal foraging theory. He loves that sort of stuff. Anyway. So anyway, there are a handful of problems in thinking sort of like evolutionary optimization. And another one is if you're a bird, how many eggs should you make? You might think, well, gee, you should make a lot of eggs because you have a lot of babies. But then you have to spread your attention around all those babies, and maybe you don't have enough attention for any of them, and they all die. So then you should just have one, but then, well, maybe then you just lavish your attention and energy and health on that one baby, and maybe it would be better to have two. Anyway, so there are like all these sorts of trade-offs, and there's some nice graphical constructions that help you think through those trade-offs in ecology that Chris Peterson, among others, enjoys. All right, so a little bit as I expected. All right, so we've got a couple of choices here. So there's one more problem that sort of from 4.3 to practice with that's actually pretty similar to problem 1. We could do that. Even if we do that, we'll still have some time. And so we could start an example from 4.5. I mean, I'm not sensing like vast quantities of energy today, so like I don't like if your energy is completely done, then we can start that on. I mean, I think we should still do problem 6. We could start that on Monday if you kind of want to get a head start on next week. We could start the next thing. I don't know. What are you guys feeling? Yeah, I think the thing I'm going to make some videos regardless, but I think the thing I want to do, I'll either do in class now or on Monday.
Could decide after the problem.
Decide. All right. So all right. Yeah. Why? Yeah. Exactly. Why decide now when we can decide later? So give problem 6 a try, and then see if that's incredibly energizing or thoroughly deflating. All right. So let's talk a little bit about this and then see what we want to do. So here's h of t. Here's this function that describes projectile motion. Our textbook may be the only book left, maybe because it's a math book, I don't know, left in the universe that uses feet per second instead of meters per second. So this would be the acceleration due to gravity. Anyway, let's see. So we want to find the critical point. So we know the function is going to look like this. This is h as a function of time. We throw the grapefruit up in the air. It goes up in the air, and then it goes down. We know that from, why do we know that? We know that because this is a negative in front of the t squared, and we know that because we've thrown things in the air, and we know they come back down again. So both physics and math tells us that this is going to, it'll be a maximum here. So let's find what the critical point is. So we take the derivative. We set the derivative equal to 0, and we solve for t. And so here I am doing that. And I'm getting 1.56. So at 1.56 seconds, the grapefruit is at the peak of its journey. So then I wonder how high that peak is. Well, we want to know what's h when t is 1.56. So we plug 1.56 into the original function. Doing that here, word has it that that's 44 feet. So at 1.56 seconds, that's the peak, the maximum height the grapefruit attains in its journey, and that's 44 feet. So some of you in past physics classes may have had to memorize formulas or even look up formulas for time of flight to maximum, or how high a projectile launched with a certain initial velocity will go. If that ever was you, now it's not you anymore, because again, you can erase that part of your memory because you just figure it out using calculus. So that's kind of fun. Are there questions on this one? All right, so I think I'd like to do sort of the thing we hadn't decided what we're going to do for the rest of class. I think what I'd like to do is something in between the two things I proposed, which is like set up a problem, but maybe not do any of the algebra for it yet. How's that for a middle of the road sort of thing? And we'll see, and then we'll find out on Monday if that's a good idea, or if I should have just done it all at once on Monday or on Thursday. So in 4.1 and 4.3, there's similar chapters. We're learning how to find critical points of functions. And for the most part, or entirely, somebody has handed you the function. Say, hey, here's a function. Would you find the critical point for this? And you'd say, sure, I know how to do that now. And you do it. You set the derivative equal to 0. You solve for x. And then you plot it to see where the points are. But of course, in real life, often you're not handed functions, but you're handed puzzles or things you want to figure out. And so 4.5, which in some ways, it's not the hardest in the sense of it's the most algebra, but it's hardest in the sense of maybe most conceptually difficult, but also the most fun and interesting, and that's OK. We're doing it at the end of the course, is looking at how you would sort of come up with your own functions to describe certain situations. So I think the title of the chapter is modeling, and what I want to do is start with an initial example that may have had some relevance, real-world relevance on Sunday or Monday. All right. So here is the situation. There is a large field, and this field is filled with snow. All right, and so let's see. And so this is going to be 600. And let's see. So you start here, and you are so 2,000 feet away, and you want to get here. What should I indicate? There's something you really like here, and so you want to get there, and that could be could be whatever you want. All right. So and along here okay. So here is a nice sidewalk. Um, and it turns out you happen to know from past experience that you walk about 4 meters per second on a sidewalk. In snow. And this is thick, goopy, wet snow that we had before. And so you actually walk about half as fast in that. And so the question is, how should you proceed? And because you want to get to this good thing, whatever it is, as quickly as possible. Yeah.
Is there sidewalk on the 600 side?
No. But that would be interesting if there was. So on the one hand, you want to spend as much time on the sidewalk as possible. Okay, so you might think, I'm going to go straight towards the thing that I really like. That's a logical strategy for much of life. But it turns out then you're spending all the time trudging through the snow. So maybe that's not so good. So then maybe, the sidewalk, I can go along really, really fast. And then I don't have to trudge through the snow very much at all. But then I'm traveling more distance. And so maybe the extra distance I'm giving myself doesn't compensate for the fact that I can go faster along this stretch. So maybe you should go for a while and then make a right-hand turn and angle through here. So, and so we're going to try to figure out where you should turn here to get to this point as fast as possible. And I want to set this up. This is, OK. So we're going to call this distance x. So x is how far you walk. Walk has an A in it. W-A. Before walk on sidewalk. On sidewalk. Before turning. OK, so a key to these problems when you're given a scenario like this is it's good to write down what your variables are, what you know, what you're given. You're going to have to introduce some variables, and you'll save yourself a lot of pain and headache if when you introduce a variable, you write down what that variable is. You might want to call this d for distance or s for sidewalk, all totally reasonable choices. Just write down what your choice is. Because as you're trying to get towards a strategy here, you may invent a bunch of other different variables, and you just want to be able to keep them straight. A large diagram is usually helpful. And I almost always find that I need to draw a diagram larger than I think I need to do. So when in doubt, I just make a big diagram someplace. So you have lots of room to scribble all over it. OK, and then label some stuff. All right, so now here's an x. And maybe I'll call that distance d. And I guess because I just told you to label variables, I should write them. It is d is distance through snow. All right. And would like a formula for d. Any thoughts on what we can do for that? Pythagoras. This is a right triangle. So this squared plus this squared better equal that squared. So this distance is 2,000 minus x. So d is 600 squared plus 2000 minus x squared square root. This full distance is 2,000. If you go x, you have 2,000 minus x left. So you have 2,000, you take away x. 2,000 take away x.
It's
Does-
like the line when you go to like the D line as you go to the person, that's where I'm getting confused.
Oh, because the person walks for a while, and then she decides to go angle towards the heart. Yeah. So x is how far the person walks, and then this is how far the person doesn't walk along the sidewalk. Yep. Okay. All right, so we're a couple lines away from having things set up. So so in general, distance equals velocity times time, or distance equals rate times time. If you know how fast you're going and you multiply that by how long you go that fast for, wow, that was a bad sentence. How long you go that fast for. Anyway, you end up with distance, how far you went. So that means that time equals distance over, oh, let's call it v. So the time it takes you to go a certain distance is the distance divided by the velocity. OK, so the total time of the journey is the time you spent walking along the sidewalk and the time you spend walking in the snow. And I think sometimes writing out word equations like this can be helpful. So you're going from this word situation and you want to turn it into equations. And so sometimes equations with symbols. But if you go from a problem to a word equation to an equation, that can be helpful. So let's see. So total time, I'm going to call that maybe capital T, total time. So time on the sidewalk, that's going to be distance over velocity. What would that be? What? Yeah, how long it takes you to walk on the sidewalk. It's going to be x on 4, yeah. All right, time in the snow. It's also distance divided by velocity. So what's our distance? Yep, that whole thing that you don't want to say, but just gesture at. Entirely reasonable. Two. Yep. All right. So now we're in good shape. We have, now I could turn this into a 4.3 problem, the problems you were just working on. I'd say, here is a function. Please find me the minimum value of this function. Right? So that's what we started off with. I handed you a function and said, find me the minimum value or the maximum value. Same thing. Right? Now I've got it into a functional form. And this is nice. There's only one variable in it, x. So what I could do, but we'll do on, we're not going to do today, is we can take the derivative of t with respect to x, set the derivative equal to 0, solve for x, and that would tell you the optimal path to take so that you can get to your desired location as fast as possible. So what I will do at the beginning of class on Monday is recap this example. I'll probably write all this junk up on the board. Actually, could someone take if someone can take a picture of these two things and then and then send it to me, then I can just recreate this on the board, and you don't have to write it down again because you've already written it down once, perhaps. And then we'll carry this through, and then you'll know how to walk through snow on sidewalks at an optimal rate. So I can stick around for a few minutes if anybody has homework questions now. And Casey's available tonight, and I'm available a bunch tomorrow.